we are discussing the design of CPU. All of you know the main part of CPU are actually two. The one is the arithmetic logic unit ALU and another is the control unit. These are the main two parts. Already we have read the design of ALU and now we started the discussion on the design of control unit. Last day we have read the basic concepts of designing the control unit, and we have seen there are two approach of designing CU, the control unit. One is the hardware control unit, another is the microprogrammed control unit. We have read last day the different type of bus architecture, that single bus architecture, the 2 bus architecture, 3 bus architecture, and using the different type of bus architecture actually that how the performance varies if we give the hardware, or actually the optimization between the hardware and the speed, that we have seen. Today we will read the hardware control design. First we see that what are the steps involved in hardware control design. Now, the step 1 is derive a flowchart from the problem definition and validate the algorithm by using a trial data. So, given a problem, the first we derive the flowchart, and flowchart means actually if a flowchart is given, that algorithm we can get from the flowchart as it is. Now, validate the algorithm by using a trial data. That means, whether it is a correct algorithm or not, or the flowchart we have got from the problem definition, whether actually it is giving the right result or not, that we have to validate. Step 2, obtain a register transfer description of the algorithm from the flowchart. Step 3, specify a processing hardware along with various components. Step 4, complete the design of the processing section by establishing the necessary control inputs. So, from here we identify the processing hardware with the components needed, and then we complete the design of the processing section. That means, what input is needed or to interface between the components and the processing section. Then step 5, determine a block diagram of the controller, because we want a hardware design. So, first we from there now the controller block diagram level controller design we have to do. Then step 6, obtain the state diagram of the controller. Once the block diagram is achieved, then from there we draw the state diagram, because it is nothing but a machine. It has some input, then it will generate some output. Step 7, specify the characteristic of the hardware for generating the required timing signal used in the controller, because the controller will provide the sequences generated in different time instances. That means, in which time instance what control signals will be generated, that is the function of the controller. So, that characteristics of the hardware for generating the required timing signal, because this is a very important thing in controller design. Then draw the logic circuit of the controller. Now, we will do the once the timing signal also we have got, hardware we have got, then the logic circuit of the controller is done. Now, based on these steps one by one, if we see the details, then we will be seeing that how that actually the control unit will be designed using the approach hardware control design. Now, we take one example. Again we will see the last day's example, that one 4 by 4 unsigned multiplication. So, already we have seen that we have to declare some registers and 3 registers are declared. Here it should be, if it is a 4 by 4, this R8 can be R4, M4, Q4. Last day we have seen that this example. Now, declare buses in bus 8, out bus 8 or in bus 4, out bus 4. So, these are 4 bit, here it is 8 bit registers, they are 8 bit in bus out bus. For 4 by 4 we can 4 bit registers and in bus out bus can be declared. Now, the actual algorithm, and this algorithm is nothing but the repetitive multiplication is nothing but repetitive addition. So, initially in the initialization portion or the start loop, that register R is set to 0 and the data of in bus is given to registers M. In the next clock, the data of in bus is set to Q register. That means, one is multiplier, another is multiplicand. Now, as it is a repetitive addition, so R is R plus M. That means, this multiplicand is will be added Q times, M will be added Q times, then it will give QM. So, R is R plus M. What we are doing, every time after this addition, Q is decremented by 1, and then if Q not equal to 0, then go to loop, out bus is R and then halt, go to halt. That means, when Q equal to 0, that means Q times it is loop, it is in loop, then it is go to halt. Now, the step 1, using this example, the 4 by 4 multiplier, simple multiplication, then we one by one we see that how the steps of the hardware control design is followed, and we can get a actual implementation of the control unit. Step 1 was derive a flowchart from the problem definition and validate the algorithm by using the trial data. See, M and Q are two 4 bit registers. Obtaining M and Q are two 4 bit registers and they contain the multiplicand and the multiplier respectively. Then product is also 4 bit, that M is of 4 bit, Q is of 4 bit and the product we say R is also 4 bit. This is the thing. The sequence of events and their timing relationships are described in the flowchart. See, we see the flowchart. First we start, then in the initialization part, this is the initialization portion. We have seen that register R is set to 0 and M is the multiplicand via in bus. Q is also multiplier via in bus. So, these two are actually the initialization portion. Now, the actual operating portion. If say if q equal to 0, so if q equal to 0, then it is program should be stopped. That means, m should be this q m is nothing but m plus m q times. So, what we have to do again here? So, we have to do that r is, we have to do here r equal to q plus m, r is r plus m. We can do that. R is r plus m. So, this is the flow chart, one initialization part, one computation part, r is r plus, computation is r plus m. Then if whether q is 0 or not, q equal to q minus 1, and then we have to see whether q equal to 0 or not. If 0, then halt, q equal, if not, then again we have to do the r equal to r plus m again. So, what we have to do here, another step, q equal to q minus 1. Now, how do we verify? Second thing was validate the flow algorithm of verification of unsigned multiplication. So, we have 3 registers R, M, Q, say these are 4 bit registers R, M and Q. Then initialization, we take some actual data. Say R is initially set to 0, so all 0. M is 0 1 0 0 means decimal value 4, and Q is 0 0 1 1 means the decimal value 3. Now, in iteration 1, R is R plus M. So, it was earlier these two will be added and result is here. So, all 0 plus 0 1 0 0, this is 0 1 0 0. M is same, no operation, then Q is Q minus 1. So, it was 3, so Q minus 1, now it becomes 2. Now, in iteration 2, again R is R plus M. So, these two are added and it becomes 1 0 0 0. M no change, Q becomes Q minus 1 1 0 0 0 1. Similarly, in iteration 3, 1 0 0 0 plus 0 1 0 0, this becomes 1 1 0 0 and Q becomes 0, Q minus 1 is 0. Then it will stop. So, the result will be 1 1 0 0, which is decimal value is 12 and it was 4 into 3. So, that is equal to 12. So, it is validated. So, the algorithm is validated. Now, step 2. Step 2 was obtain a register transfer description of the algorithm from the flowchart. So, again using the same example of multiplication, R is set to 0, M is in bus, Q is assigned to the data of in bus, and then this loop is R is R plus M, Q is Q minus 1. If Q not equal to 0, then go to loop, out bus is R, hard, go to hard. So, actually what algorithm we have decided, the algorithm we have read, it is there, the register transfer logic. Now, the step 3, the processing section. Step 3 was specify a processing hardware along with various components. So, the processing section contains 3 main components. One is general purpose registers. So, 3 operation clear, parallel load and decrement can be performed by applying the inputs at C, L and D. If we remember the operations, one is R is set reset, the register R is set to 0, one is R is set to 0, that is clear. Parallel load is M is in bus and Q is in bus, that is the operations. The multiplicand and multiplier should be loaded. Another is decrement, Q is Q minus 1. So, these are my operations to be done. So, these 3 operations are performed by applying the inputs at C, L and D. Now, another component is a 4-bit adder and a tri-state buffer. So, these components are like that. One is the general purpose register. So, this is the general purpose register, one clock is there, this is a 4-bit input, 4-bit output, and these are the 3 inputs C, L and D. So, CLD, the if we see the operations of these 3 inputs. So, these are the values of CLD. When C value is 1, LD 0 0, then the clock, say if it is a trailing edge triggered, then action is the clear, action is clear. Now, C is 0, L is 1, D is 0, clock is trailing edge trigger. This is load external, operation will be load external data, load external data. Now, 0 0 1, so again it will be the decrement, operation is a decrement by 1, decrement by 1. If it is 0 0 0, CLD, clock is a trailing edge, operation is no change, this is a no change. So, these are the 3 inputs. Now, another component is a 4-bit adder. So, already we have read this is a 4-bit, 2 4-bit operands and the result is a 4-bit. So, if the control input comes, say the control input is for this thing, the control input either 1 or 0. If it is 1, then the function is, say, two things are added, I plus r. If it is 0, no operation, no operation. Now, another is a tri-state buffer. So, again if it is a 4 bit tri-state, one control input and the control input either it will be 1 or 0 and the output will be either 1 is, when control input is 1, then it is whatever input it is coming, or high impedance. When it is 0, that high impedance state, when it is 0, it is a high impedance state. So, this is the design of the three main components. Now, step 4. The step 4 was the complete the design of the processing section by establishing the necessary control inputs. Now, we see the detailed logic diagram of the processing section along with the control inputs. We have seen the 3 registers M, R, Q. The R is a register, M and Q are the containing 2 registers containing the multiplicand and the multiplier. Now, R is R plus M. Initially, R is set to 0 and then R is R plus M. So, one 4 bit adder is needed and Q is Q minus 1, that is to be done, and then it is to be checked that how many times it will be added. So, we need this. This is the detailed logic diagram of the processing section. So, all these buses will be 4 bit, because this we are illustrating the 4 by 4 multiplier. Now, these are for M bit, these are L and then C, D, these are grounded. This should be CL, D should be grounded. Again these values should be coming from here, from outside, CL, not from here. Now, these are L, D and C. So, actually that 3 operations it will be doing. One is R is set to 0, then M is in bus, Q is in bus, assigned to in bus means data multiplicand and multiplier are loaded. Then R is R plus M, R is R plus M and Q becomes Q minus 1, and then it will be checked whether Q equal to 0 or not. So, this is the processing section. Now, step 5, determine a block diagram of the controller. Now, the controller has 3 inputs and 7 outputs. The reset input is asynchronous. The clock input is synchronized to the controller's action. All activities are assumed to be synchronized with the trailing edge of the clock pulse. So, this is my step 5. So, what will be the controller design? So, controller has one input is reset, controller one input is reset, this is a Z input, this is a clock, and 7 outputs, these are 7, these are the outputs. Now, we have to see that step 6 will be the state diagram of the controller. The controller must initiate a set of operations in a specified sequence. Therefore, it is modeled as a sequential circuit. So, the state diagram of the unsigned multiplier controller we can draw in this way. Say these are the different states T0, T1, T2, T3, T4, T5. Now, initially the controller is in state T0, this is the initial state. Now, at this point the control signal C0 and C1 are high, C0, C1 equal to 1. Now, operations R is reset, R is clear, and M assigned to inverse are carried out with the trailing edge of the next clock pulse. So, the controller moves to state T1 with this clock pulse, that means after initialization, after one clock pulse, these two operations that are set to 0 and M set to inverse, these two operations will be followed in this. Now, say this state is the controller moves to state T1. When the controller is in state T2, then R is R plus M and Q equal to Q minus 1, these two operations will be performed. Now, all these operations take place at the trailing edge of the next clock pulse, and the controller moves to state T5 only when the unsigned multiplication is completed. So, this is the last state. The controller then stays in this state, and a hardware reset input causes the controller to move to state T0 and a new computation will start. Now, we see in this state diagram the selection of states, how the selection of states is made. See, there are we take the control state, operation performed, and control signals to be activated. Just now I mentioned that at T0 state this is initialization. So, R is reset to 0, M is inverse, and then C0, C1 should be high. At T1 state, Q is inverse, Q is inverse, and then C2 is high. T2, R is R plus M, Q is Q minus 1, say C3, C4, C6, these 3 will be high. Then T3 none, T4 is R is good, R goes to out bus, means the result goes as a output, and then C5 is high. T5 means it is completed, operation is multiplication is completed and nothing could be done. So, none, none. So, these are the control signal to be activated. So, from the state diagram we get this information that these are the control states, and then I have to get this control signal to be activated, means these control signals should be high, and when these control signals should be high, then these operations should be performed. So, we get this information. Now, how the states are selected in this state diagram? Now, if the operation are independent and can be completed within one clock cycle, then they are grouped within one control state. Example is that R, if R register is reset to 0 and M is set to multiplicand, that means data, that time the data contained in the in bus, then these two are actually independent, no one is affecting. So, these are grouped together and they are in one state. Conditional testing normally implies the introduction of new states. So, Z introduces a new state T 3. Now, we see the previous, so this at T 3 state, this is actually we are checking whether q equal to 0 or not. Now, if q not equal to 0, then actually we will go back to T 1, that means again we have to perform R equal to R plus M, q equal to q minus 1. So, this should go here, not this T 1, because this is a reset state. This is a this should go at T 2. Then if Z equal to 1, that means that other condition is q equal to 0, then it goes to T 4 state. That means it is it denotes that that R is in this T 4 state, this T 4 state actually outbus becomes the R, outbus is assigned as R and T 5 is nothing could be done. This is already the operations of multiplication is completed. Now, one should not attempt to minimize the number of states, as correctness of the control logic is more important than the cost of the circuit. So, for the first case, for the initial design of control unit, we will not minimize the number of states, as it is a machine. So, we can do that state minimization, but as correctness of the control logic is more important, that is here our aim is not actually the minimization, but to get the actual correct design of the CU. Now, step 7, the generation of time signal by control unit. See, one of the main tasks of CU is to properly sequence a set of operations such as sequences of n consecutive clock pulses, and timing signals are normally generated from a master clock. So, 6 non-overlapping control signals must be generated, as there are 6 states in the controller. Now, we see one example that how the timing signals are generated. See, we have one master clock pulse. So, there are 6 states in the controller state diagram. So, 6 non-overlapping timing signal T0 through T5 must be generated, so that only one will be high for a clock pulse. Now, here we have shown that 4 timing signals T0, T1, T2, T3, T0, T1, T2, T3. Say this is a master clock pulse, this is my master clock pulse, and say this T0 clock pulse, this is a different clock, and when it is high, say here that this T0 is high at the trailing edge of the master clock pulse. After the first clock, the trailing edge of the master clock, it becomes high, and again it is high up to the next trailing edge of the master clock pulse. So, in this way it will, this is one high, and then 1, 2, 3 clock pulses. After 3 clocks of the master clock, it becomes low. So, that means in 1 clock pulse of the master clock pulse it becomes high, and for 3 clock pulses it becomes low. In this way it will be the T0 will be of that type. Now, T1 is only in the second clock pulse, say in the, this is a 1, that means T0 becomes high, and just the T0 at the trailing edge of the T0, T1 becomes high, and it is only for 1 clock pulse of the master clock pulse, and then again it becomes low. Similarly, at the trailing edge of T1, T2 becomes high, and it will be high for 1 clock pulse of master clock, then it becomes low. T3 is similarly at the trailing edge of T2, it becomes high, and again it becomes low after 1 clock pulse of the master clock. So, in this way T0, T1, T2, T3 can be generated. So, this is how from the one master clock the other timing signals can be generated in the control unit design part. Now, the logic circuit of the controller, the step 8. What will be the logic circuit of the controller? So, first we see what will be the, so far we have discussed the starting from the flowchart, then algorithm, then the hardware components identification, then the state diagram, and from the state diagram that what will be the timing signals can be generated, and now we see we have to combine the whole thing and the what will be the logic circuits of the controller. Now, the key elements of the implementation is the sequence controller hardware, which sequences the controller according to the state diagram. Already the state diagram we have drawn. We know that what output should be generated, that then at that clock what control signals will be, what control signals will be high at what time state, that also we have derived. Now, all the things will be, all the steps so far we have discussed, that must be combined in this step 8 to get the actual logic circuit of the controller. Now, see, this is the key thing is that the key element of the implementation is the sequence controller. So, the controller, so it is the first is the one mod 8 counter, one sequence controller, one 3 to 8 decoder. This is the whole thing of the logic circuit. Okay. So, if we complete the whole design, so mod 8 counter, it has, we have already seen that enable, clear and load. So, say this is enable when this line is high, then it is a reset line, this is a reset, this is a load line. So, these are enable, this is a clear, this is a load, and the 3 outputs, say the 3 outputs are O0, O1, O2. This goes to a 3 to 8 decoder, and the other inputs from the sequence controller, one is L, one is, and the other 3 are say 3 D2, D1, D0, and 3 to 8 decoder. So, these 8 from here we have seen there are 5 states. So, these are actually T0, T1, T2, T3, T4 and T5, and the rest 3 are actually unused. These 3 lines are unused. Now, already we have seen, we have derived that at T0 the control signals should be high there, C0 and C1. So, if we write clearly, say actually at T0 state C0 and C1 control signals should be high. Then at T2, C2 is high. Similarly, we have seen T3, C3, T3, C3, C4 and C6, and T4 there is C5. These we have seen already, T0, T1, T2, T3, T4, T5, that these control states, this control signal should be activated. Okay. So, this signal, so C0, C1, C2, then C3, C4, C6, then C5, and at T5 it will be the C6 at T4, and they so this control signal should be high, and these are, this is another Z input, and this should be that these 2 inputs are coming from the T3 line and the T0, T1, T2, T3, T4, T5 line. So, T3 line and T5 line, this will be, these 2 are added. So, these are the logic diagram of the unsigned multiplier. Now, the logic involved in deriving the entries of the sequence control truth table, the mod 8 counter is loaded or initialized with the specified external data. Just now we have seen that the enable, clear and load line. Now, the input L provides the counter enable control input E, already we have seen. Now, from the controller state diagram, if we see again the controller state diagram, the controller counts up automatically in response to the next clock pulse. Every clock pulse it is in the next state. When the counter load control input L equal to 0, because the enable input E is tied to high, such normal non-sequencing activity is desirable. Say the present control state is in T0, then the present control state T3 and Z equal to 1, the next state will be, say if the present control state is D0 T0, then in the next clock pulse it will be in T1. The operations assigned or defined at this state will be performed. Then when the next again clock pulse will change, the next clock pulse it will be in T2. Operations will be performed at this stage, defined in this stage. Then it will be in T3 and parallelly the conditions to be checked, that means Z equal to 0 or Z equal to 1. If that T3 and Z equal to 1, present control state is T3 and Z equal to 1, then only in the next clock pulse it will be in T4, this state. And if the present control state is T3 and the condition Z equal to 0, then the next state is T2 instead of T4. So, these are my control signals, that means present state and the input. So, here the input is the conditions, the signal generated after the condition, and then the machine will change. So, from the controller state diagram, say if the present control state is T3, the counter output will be that O0, 1, O2. So, these are the O0, 1, O2, these will be 0, 1, 1. So, when the state is, say when the state is T3. Now, and if Z equal to 0, the next state is T2. When these conditions occur, the counter must be loaded with external value 0, 1, 0 at the trailing edge of the next clock pulse. The T2 equal to 1 only when O2, O1, O0 is 0, 1, 0. That means T2 is 1 only when O2, O1, O0, these are 0, 1, 0 value, it will take. Therefore, the SC generates L equal to 1, the load value equal to 1 and O2, 1, O0 equal to 0, 1, 0, it has to generate. Now, similarly from the controller state diagram, if the present state is T5, if we see, if it is T5, the next control state is also T5. The SC, the sequence controller, must generate the outputs L equal to 1 and D2, D1, D0 is 1, 0, 1. So, the SC truth table shows these out of sequence counts. For each row of the SC truth table shows that what output value should be generated by the SC controller, and accordingly the design should be like that. See if we see the logic circuits. Now, first we see the truth table. We will see the truth table. Truth table of the logic circuits. This is the truth table. So, this is Z, T3, T5 and outputs are L, D2, D1, D0. Now, Z is 0, say if T3 equal to 1 and T5 we do not know, T3 we are seeing. then actually output should be L equal to 1 and D2 D1 D0 is 0 1 0, just now we have seen. Now, if T5 equal to 1, then it should be in the same state. So, again L is equal to 1 and D2 D1 D0 is 1 0 1. So, in this way the output input output values, that means the truth table will be computed. It can be completed with the all other states, that means when T what will be the T3 T5, then what will be the T4 T3 T2 T1, and when everyone will be 1, say T4 will be 1, then what output value will be there here. Similarly, when T3 equal to 1, what output value will be generated here. T2 is 1 and T1 is 1, then we have to what output values. So, these are my, that if these are the inputs, then what output will be generated by my SC controller. Now, if we see the logic circuits, if it is a PLA design, then actually the L can be P0 plus P1, D2 equal to P1, D2 the 4 outputs L, D2, D1, D0. So, L is P0 plus P1, D2 is P1, D1 is P0, D0, and the control states are related to the control signals as follows. Say C0 equal to C1 is T0, C2 is T1, C3 equal to C4 equal to C6 is T2, because if T2 is high, these 3 signals should be high. At T4 state C5 is high. So, when the controller is in state T0 or T2, multiple micro operations are performed, this T0 and T2, T0 and T2, these two. Now, when it is in state T1 or T4, a single micro operations will be performed, that means at T1 and T4. So, if it is a PLA design, then this type of AND array and OR array circuits will be there, and the logic we can write that the product term is generated in the PLA design as P0 plus Z bar T3 and P1 equal to T5, sorry, P0 equal to Z bar T3 and this is P1 equal to T5, and then this the output signals will be generated. So, we have seen that in this way we can design the control circuits. Now, these last 2 classes we have mainly discussed about the control unit design. So, the quiz on lecture 36-37 is the first is what is the purpose of control unit in a microprocessor, and draw a logic diagram to implement the following register transfers. If the number in the 8-bit register R is negative, then x is x minus 1, else x is x plus 1. Assume x is 8-bit wide. So, this register transfer, what will be the logic, and state the merits and demerits of single, 2 and 3 bus architecture inside a control unit. So, this is actually the part of the register transfers, one steps of the ALU, that a logic diagram to implement the following register transfers. After the flowchart derivations, the step 2 was the obtain a register transfer description algorithm from the flowchart. So, this as if step 2 is given, x is x minus 1 and x is x, else x is x plus 1. if r is negative, then x is x minus 1, if r is positive, this is. Then what will be the hardware for this, the logic diagram for this, the control unit for this type of logic. So, this is a simple very primitive control unit design, and that is the quiz question of lecture 36 and 37. Actually, we have discussed the multiplier 4 by 4 multiplier. Instead of that, we want to design this CU. So, this is the end of this class. Next day we will discuss the other thing. We are discussing the design of CPU, and in last class we have read the design of one type of control unit called the hardware control unit. Today we will read the other one, the microprogrammed control unit. So, first we see what do we mean by microprogrammed control unit, and then we will read the design of that particular type of control unit. Now, microprogrammed control unit contains the programs, and this program is nothing but a set of micro instructions. Now, programs are stored in a control memory, normally in a ROM inside the CPU. Now, to execute instructions, the microprocessor first fetch each instruction into instruction registers from external memory. Then the control unit translates the instruction. Each control word contains signals to activate one or more micro instruction. After translating this instruction, then the control unit decides or activates the control signal that what particular operations to be executed. Now, a program consisting of a set of micro instructions is executed in a sequence of micro operations to complete the instruction execution. As this microprogram is nothing but a set of micro instructions, so it is very much important that what will be the format of this micro instruction, so that this sequence of micro operations or micro instructions to be read to control the micro operations. Now, all micro instructions have two fields, one is control word, another is next address. Now, this control word